Welcome to Lecture 12.1, Introduction to Parallel Computing for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you'll have an understanding of what parallel computing is, how parallelization is useful, how to write parallelized loops, and some of the limitations of parallel computing in MATLAB. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. Up to this point in the semester, we have been writing serialized code, where each operation is processed in series, meaning one at a time. Parallelized code executes multiple operations simultaneously by taking advantage of how computer processors are built. Let's briefly explore this architecture. The central processing unit, or the CPU, is your computer's brain. Every operation that happens on your computer passes through the CPU, even if it isn't actually calculated there. It handles arithmetic and logic, managing memory, planning execution order for processes, and so many more things. Modern computer processors contain several of these CPUs, which are commonly called cores. Each core operates independently. At any given moment, your CPU cores are running tons of operations to keep your machine going. Here's some of my CPU activity at the moment. You can see a graph of the activity for all of the different cores doing their operations. Now, the code that we have written this semester all utilized just one core. We can accelerate our code by distributing it across more than one core, thereby parallelizing its execution. By doing this, we can reduce our code's execution time by a factor approximately equal to the number of cores being used. This enables really large studies that would otherwise take far too long. This is also the foundation of supercomputing, incidentally. Recall that for a regular for loop, we write it as follows. We use the for keyword and then our indexing variable from 1 to 8, and we print that out in a string. And we see the following output where it indexes from 1 all the way up to 8, just like we expect. The par_for keyword can initiate a parallelized loop instead. Here we see all we do is change the for loop into a par_for loop with exactly the same code around it. This produces the following output where we see it starts up the parallel pool first, and then it has connected to one with 8 workers, and then we see the string output from 2, 5, 4, 7, 3, 1, 6, 8. That is different. Now, the serialized version performed exactly what we expected it to do, printing out each incrementing number from 1 all the way up to 8. But the parallelized version did not do that. This is because the processor distributes the iterations of the loop across the available workers, 8 of them in this case. All 8 cores print their text at roughly the same time. But in reality, only one core is given access to write its output at a time. Even more interesting, the printing order is inconsistent with each subsequent run, meaning when we initialize the first parallel pool, we get a first order. We initialize a second parallel pool, the order completely changes. And again, for a third parallel pool, it's completely different as well. Here we can see that the workload gets distributed and executed differently with each new parallel pool. Now, to put these things together, let's return back to the parametric sweep from Lecture 10, where we studied the Warren truss. We'll add a timer, and we'll use the par_for keyword, the code for which is on the next page, in order to study these things. So we end up with the following output, where the length of the thetas array is 89, and our serialized loop time is 1.2378 seconds, but our parallelized loop time is actually 1.3515 seconds. It's slower than the serialized time. What happens if we increase the problem size? Here's the code. If we increase the problem size, then we actually get this table. We see on the left-hand column the number of values we're testing for theta. That's increasing as you go down the table. And then the runtime values for the serialized and parallelized implementations in the middle two columns, and the ratio between those things all the way in the far right. And we see as we go down the table that the ratio actually increases with the more test cases that we're running. We can visualize this with a plot. And we see here that on the left-hand side, the runtime itself increases just like we'd expect for bigger problems. But if we take a look at the ratio graph, we see that the ratio between the serialized speed or time and the parallelized time starts to level off. It's approaching a factor of 8, which, like I said before, is the number of workers on this computer. This is an effect called Amdahl's law. You are welcome to take a look at it in more detail if you are interested, but this places a bit of a limitation on parallel computing for small problems. Now, the parallelized code power stems from extremely large problems like parametric sweep studies. As we've seen, the effects of parallelized code become more pronounced as the problem size itself increases. We have seen a hint of this already, but at this point you might be wondering if there are any downsides. Yes, there are. MATLAB first has to initialize the pool of workers before the cores can execute any of that code, which takes about 12 seconds on my computer. I've completely neglected to tell you about this part of the process so far. For small problems, this initialization alone likely takes longer than the serialized implementation of the same code. In fact, it does take longer than a couple of the implementations for the example before. But as the problem increases in scale, this initialization becomes negligible. Compare the 12-second initialization to the 1,000-second test from our example before. Then in addition to the initialization process, there's also overhead for just managing the parallel processes themselves. MATLAB has to decide how to segment the operations and manage each core's access to memory, among other things. These things require some compute overhead, which is much more noticeable for small problems. Recall that the runtime actually decreased, going from the number of theta values is 89 to 177. That is a manifestation of this fact. And lastly, for parallelization of loops like we see here, the iterations cannot be interdependent. Each core simultaneously executes different iterations of the loop, so it will fail if the 10th iteration, for example, depends on data from the 9th iteration. With that said, there is a whole field dedicated to solving this. If you're interested, consider taking a distributed systems course because this can get quite interesting. Now to summarize, parallel computing is executing code using multiple processor cores. Large problems can be dramatically accelerated by distributing the execution across multiple cores. That's why it's useful. In order to do that, in MATLAB, we use the par4 keyword to transform a regular loop into one that can utilize multiple cores, but there are limitations. Notably in MATLAB, the overhead from both initializing the pool and managing those cores during the execution process. And of course, the iterations cannot be interdependent as we just discussed, or the parallelized code will fail.